previous two videos we used were about the product rule, the quotient rule, and some of the trig functions that we can find the derivatives of using those. This next one is called the chain rule. I'm going to make several videos about this because it is probably the most commonly used rule throughout all of calculus. We will refer back to it when we're doing antiderivatives as well as derivatives here. So the first thing that we need to understand is that the chain rule will be applied when we have a composite function. In other words, a function that's embedded inside of another. We've seen the composite function notation as f of g of x or f fog, with the little circle. We won't be thinking of it in that sense. We're going to be thinking about it with the parentheses. What we need to recognize is that it won't be written in that f of g of x notation. We're going to have to kind of look into it and recognize that composite functions are usually going to have parentheses in them where there's a chunk of stuff that is inside the parentheses. So a plain function here is 5x to the 7th, but I have inside the parentheses a power raised to another power here, so that's a composite function. Similarly, I have sine of x as a plain function, but as soon as I change what's inside the trig function, now I have a composite function. And then the last one here is cosine cubed of x. That is technically a composite function because really this is equivalent to, it's written up above, but I'll write it again, cosine of x and then cubed. And so the cosine is getting evaluated and then cubed. The chain rule written in notation here is that if I have a function inside of a parentheses raised to a power, then what I'm going to do is apply the power rule. So again, I swing the n in front and I decrease the exponent by 1 as denoted right here. And then I take the derivative of what's on the inside of the parentheses. So you'll hear me say, take the derivative of stuff. In terms of function notation, what you're going to do is you're essentially working your way from the outside in. So the outermost function here is f. So I take the derivative of f. So we'll call that f prime. Now what's inside is preserved. So it's f prime of g of x. And then another reason it's called the chain rule is there's links in the chain. So we have to multiply by the derivative of what's on the inside. And so we multiply by what's on the inside is g. So the derivative of that would be g prime of x. So let's go through a few examples here. So if I'm working my way from the outside in, on this first example here, I've got an exponent of 5 as the outermost thing. So I'm going to first apply the power rule, swing that in front. So I have 5 times, and then what's inside is preserved. So 5 times the parentheses, and then I decrease the exponent by 1. So there's the power rule. But then I also have to remember, again, this was the chain rule, so I am now multiplying by what's the derivative of on the inside here. So it's going to be 12x squared plus 3. And this is a lot simpler than multiplying this parentheses out 5 times and applying just the simple power rule for that one. So we have another example here of the fractional exponent. So again, if I apply the power rule first, the outside thing is the 2/3. So 2/3 x to the 4th plus 2. And then I decrease the exponent by 1. So 2/3 minus 1 is negative a third times derivative of the stuff. The stuff is what's on the inside of the parentheses. So we're looking at times 4x. Parentheses not important for this one as much as was the previous one because the derivative of the stuff was a 2-term expression. Here it's just a 1-term expression. Again, we're just going to leave it like that. Other possibilities that you could see for an example like this is rewriting it in a radical notation with positive exponents only. Okay, so example C. You could apply the quotient rule here, or you could recognize that this is really the same as -7 parentheses 2x minus 3 to the -2. So it's a lot easier than doing the quotient. So if I swing the exponent in front, -7 times -2 is 14. 2x minus 3, so the stuff stays preserved. Now to the -3 because I decreased the exponent by 1. And then I multiply by the derivative of what's on the inside of the parentheses here, which is 2. And so I could multiply the 14 and the 2 together as a final answer. If it was multiple choice, you might see that happen where you might actually write your answer as 28 parentheses 2x minus 3 to the negative 3, or perhaps even 28 over 2x minus 3 in parentheses cubed, like that. And again, free response question, you are perfectly fine leaving it like that. If not, you might want to go and see how you could algebraically manipulate it for a multiple choice to match one of the answers. All right, so the last one we'll do here before we get into trig is recognizing that this one is going to be equivalently, I could write it as 5x parentheses x squared plus 2 to the negative 1/3. So this is not the derivative yet. All I've done is rewritten it so that I could apply different rules. Now you could have actually done the quotient rule, and that's kind of the interesting thing is you don't actually have to memorize the quotient rule. You can do this one. You can rewrite every question, now that we know the chain rule, as a product rule question. So you could see how this is going to work here. If I do the product rule here, derivative of the first is 5 times the second. So it's x squared plus 2 times negative a third. Again, I'm not taking the derivative of the parentheses yet, because I'm only taking the derivative of this. So I'm doing the product rule and combined. Maybe I'll highlight it here. So this is one of the functions, and this is another function. So the derivative of the yellow was 5 times, I don't take the derivative of the blue, plus, now I do the derivative of the blue, so I'm going to have to do the chain rule when I do this. Negative a third times x squared plus 2 to the negative 4/3 times chain rule, right? I still haven't taken the derivative of what's on the inside of the parentheses, 2x. So now I've finished taking the derivative of the blue stuff, times 5x. So this is kind of an interesting example. I'll show you how this actually comes out to be the same thing if we did the quotient rule. Okay, so I'm going to change my colors up here. And now I'm going to do this using the quotient rule. So low, D high. Low, D high is going to be the bottom, which is, maybe I'll rewrite this first, is 5x over x squared plus 2 to the 1/3 right now. So low is this, D high, which is 5, minus high, D low. So the derivative bottom would be x squared plus 2 to the negative 2/3 times 2x. So that's the D low part, all over the low squared. So we're looking at x squared plus 2 in parentheses to the 1/3 squared. So now it becomes to the 2/3. And it might not be obvious, but that is actually the same thing as what I have over here by a little bit of algebraic manipulation. So what I can do is I'm going to rewrite this. So if I multiply the top and bottom, perhaps, let's say I put this one over 1 and multiply the top and bottom by x squared plus 2, x squared plus 2 to the 2/3, right? Because the denominator in the blue one here is x squared plus 2 to the 2/3. So let's see what happens if I do this. So if I distribute, now I have x squared plus 2 to the 2/3 times x squared plus 2 to the negative 1/3. When I add those exponents together, I get 5 x squared plus 2 to the 1/3 plus, or minus technically, right? Because I got a positive times a negative. So I have minus let's see, so we have 1/3 x squared plus 2. If I distribute that to there, 2/3 plus negative 4/3 is now going to be x squared plus 2 to the negative 2/3. And then the 2x and the 5x can multiply together and be 10x squared. And again, this is all over that denominator of x squared plus 2 to the 2/3. So I'm running out of space here, so I'll write it off to the side, x squared plus 2 to the 2/3. Now, these answers are not the same, and I realized that when I did the chain rule, I messed up over here. When I took the derivative, when I did high d low, I forgot to put a 1/3 in front over here. So this should really be a 1/3 front there. So I messed that up. So it's always good to check your work if you have time. But now you can see that those are the same because we have 5 times x squared plus 2 to the 1/3, 5 times x squared plus 2 to the 1/3, negative 1/3. The 5x and the 2x multiplied together to give me 10x squared. So that's what makes these questions hard, especially when they're multiple choice, trying to figure out how to match your answer to the answers that are there. All right, so now let's apply chain rule to trig functions. The expectation is that we have the basic derivatives of the 6 trig functions memorized. Derivative of sine, tangent, and secant are all positive. Derivative of sine is cosine, tangent is secant squared, and secant is secant u tangent. For the trig functions that are co-functions or start with a c, those are all going to be negative in front. All right, so there's kind of a trick to help you memorize those. So when I'm doing chain rule with a trig function, working my way from the outside in, see the outside function here, and this composite function is the cosine. So the derivative of cosine, we already know, is negative sine of stuff, 3x, right? I haven't taken the derivative of what's on the inside. Then I've got to remember my links in the chain here, so I have to multiply by the derivative of what's inside the parentheses, which is 3. So negative sine 3x times 3. If you want to practice F and G right now, go ahead and pause the video, but I'm going to go ahead and do them. Derivative of sine of 5x squared, derivative of sine is cosine. I haven't taken derivative of what's on the inside yet. And now I multiply, right? It's called the chain rule because we're multiplying by the links of the chain. So we have cosine of 5x squared times the derivative of what's on the inside of the parentheses, which is now 10x. Last one, cosecant of 7x to the 5th. Derivative of cosecant is negative cosecant stuff, right? And you can't have a trig function without putting anything in it. So these are what u's are here, 7x to the 5th. So negative cosecant of that, cotangent of that stuff. So there's that times the derivative of what's on the inside here, which is going to be 35x to the 4th. Where it gets even a little bit more complicated are ones where we have exponents on our trig functions. So if we have an exponent on a trig function, you need to recognize that the exponent is really the same thing as saying the cosine of 5x to the 4th. So that exponent is on the trig function. That's the first thing we need to take care of. So this one's going to have 3 links on the chain. First, we swing the exponent in front. We do 4 times the cosine of 5x to the 3rd. All right, decrease the exponent by 1. So cosine cubed of 5x. So I've taken care of the exponent. Here's the first link of the chain. Times, now I've got to take care of the derivative of the trig function. So that's going to be negative sine of 5x. So taking care of the trig function now, so that's the second link of the chain, times 5. And we can multiply that all together and simplify it if we wanted to. The 5 and the 4 could multiply together, and we could call this 20, or I guess the negative as well, so negative 20 cosine cubed 5x sine 5x. Okay, so let's try the next one. Secant squared of 4x cubed plus 5. So first we have to take care of the exponent. Bring the exponent in front, decrease the exponent by 1, so now secant to the first of 4x cubed plus 5. Now we have to take the derivative of the trig function. The derivative of the secant is secant tangent, so we have times secant of stuff tangent of stuff. And then the last link of the chain is multiplying by the derivative of what's on the inside of the parentheses, which is the 4x cubed plus 5. So that's 12x squared. Again, we could clean this up. I recognize that we have secant of stuff and secant of stuff, and there's the same thing inside these parentheses, so I could actually write this as 2 secant squared 4x cubed plus 5 tangent 4x cubed plus 5. And while I'm at it, I could actually multiply together the coefficient in front. This is usually what you'll see as a multiple choice answer, is multiplying that coefficient with the variable term 12x squared. We'll actually have 24x squared in front. So if it was multiple choice, chances are the multiple choice answer would be written like this. All right, 2 more. Tangent of sine x. The outermost function is the tangent. So derivative of tangent is secant squared of stuff, right? I'm only going from the outside in. Next link of the chain is multiplied by the derivative of what's on the inside. And so that would be cosine of x. Trig can be kind of challenging because it's hard to see that these are composite functions usually. Right? Unless it's just a trig function with an x inside of it, it's pretty much always going to be a composite function. Last one is more of an analytical approach. You're not given an actual equation or expression for a function, you're just given information about derivatives. So we have h of x is defined as f of g of x, find h prime of 3. So h of x is, or h prime of x, again, remember we can't plug in 3 yet, is f prime, right, from the outside in, f prime g of x times, now the link of the chain here, g prime of x. So h prime of 3 is going to be f prime of g of 3 times g prime of 3. So we have numerical values we can plug in here. We're looking at f prime of g of 3 was given as 4 times g prime of 3 was given as -5. F prime of 4 we can now find as 8. So we have 8 times -5. So our final answer is -40. So we have some extra information that was not necessary in terms of answering this question. And they always like to do that. Okay, that's the first day of the chain rule.